Okay, in our last class, I introduced about the magnetism by there are many permanent magnets, and we can generate magnetic field by the running current. And also, I explained if we have a moving charged particle, they exhausted some force called the Lorentz force because of the magnetic field. And if we have a electric field, we have a total force from the electric field and the magnetic field. And we learn about the magnetic dipole moment, which one is quite similar to the electric dipole moment. And also we learn about the susceptibility, which one is the response function of the materials for the electric field or the magnetic field. And we learn about the magnetic flux density, and we learn about the various physical quantity in the magnetism, like magnetization and magnetic flux density, magnetic field, and also we learn about the magnetic moment and various units. And I just briefly talked about the Maxwell's equation, which was the very fundamental one in electromagnetism. And I assumed all students attended this class are already familiar with this Maxwell's equation. And we focused on the Biot-Savart law to calculate the magnetic field from the running current, or Ampere's law, which one is more useful when we have a higher symmetry system. So from the Biot-Savart law, we can calculate magnetic field from running current using this differential form. By taking the integral, we can obtain the total field from all this running current. But generally, that is not easy task because the numerical calculation requires a lot of knowledge about the integrals, and sometimes it is impossible by hand. We need some numerical calculation using the computer. Fortunately, nowadays, the computing power is very, very powerful, and there are many good software you can do it very easily. And for the simple case, for example, infinite long wire case, calculate the magnetic field very easily by the Ampere's law, and we can do it by hand. Maybe we need just a single line of the equation like this. Or if you want to generate magnetic field using the wire strip, and you can calculate the B field by Ampere's law again. And if you have a solenoid, which one is very widely used circuit element in many applications, and by the assumption of the well-packed combination of rings, we assume the magnetic field exists only the inside of the solenoid. And if we take the Ampere's law, we can easily obtain the relation of the magnetic field and the running current and the number of turns per unit length. Okay, that's the very brief summary of the last day's talk. This view graph explains about the 4 types of the material in magnetism. We can divide such kind of diamagnetism and paramagnetism, ferry, anti-ferromagnetism, depends on the response of the material to the magnetic field. So I just to explain the ferromagnetism is most important in application, but sometimes ferry or antiferro is also important. But in the sense of the magnetism, diamagnetism and paramagnetism is rather less important. But we should understand what is the diamagnetism and paramagnetism. Sometimes it is important. For example, for the diamagnetism, this diamagnetism response means when you apply the magnetic field, we have a negative magnetic moment. That means the magnetic moment is opposite to the external magnetic field. And that can be happen in any kind of material, all the materials, because all material has a orbital motion of the electrons. And this orbital motion of electron is the one of the reason of the diamagnetism. But the effect of diamagnetism is very, very small. So if we play with ferro or paramagnetism, usually it is ignorable. It is very small. But in some case, like a superconductor, which one is called the perfect diamagnetic material, diamagnetism is, the effect of diamagnetism is very large. So maybe you heard about the Meissner effect, which one means superconductor can refill the magnetic field to the outside of the superconductor. Because of this Meissner effect, you may see the superconductor is let's say there are very strong repulsive force between the the superconductor and the magnetic field. So there is some hovering effect, kind of levitation. And if set this diamagnetism, usually most material also has a paramagnetism. That means if we have just assume some material and they have electrons inside of the materials, and the direction of spin is quite random. But if we apply the magnetic field, the alignment of each spin, they are not perfectly aligned, but they try to align some field direction, and the average of the spin direction has in a zero field, the average of the spin direction is 0. They are perfectly isotropic. But if you apply the certain amount of magnetic field, the spin starts to align to the spin direction in a small portion. So there is a finite moment to the direction of the field. And this projection or the average value to the field direction is getting increased by increase the magnetic field. And usually they are linear. The alignment of the amount of the alignment of the spin to the field direction, they are called the magnetic moment, linear to the external magnetic field. So we have a constant susceptibility. And this susceptibility is very, very small. So usually 10 to minus 5 something. That means if you apply very, very strong field, then we got a small amount of alignment. That's the called the paramagnetism. And ferromagnetism, which one we will learn for next 2 or 3 classes, they are very unique feature in a solid state in many sense. And if you understand what is a ferromagnetism, you can easily understand the ferri and the antiferro also. So in this graph, we explain the diamagnetism and the paramagnetism. And what is the ferromagnetism in this sense? Ferromagnetism means even we didn't apply the external magnetic field, they still already have a certain amount of magnetic moment. That's called the spontaneous magnetization. And we will learn why that happens. Okay, during my lecture, if you have any question, please raise your hand, and I will allow to use your microphone, or you may ask a question by the chatting mode. Okay. In a previous class, I already mentioned about what is the ferromagnetism very briefly. Ferromagnetic material means if we have a atomic moment, means each atom is very small, tiny magnets. That's the called atomic moment. Actually, they came from the spin, the spins of the electron. Well, let's say that's the atomic moment. And in a previous page, I expressed this small arrow, and they call the atomic moment or the moment from the spins. It's same in the sense. So in the ferromagnetism, this atomic moment have a long range ordering. That means the ordering means they have some correlation. Means if one spin, one atomic moment pointing one direction, the other one has the same direction or related direction, means the ordering. And the long range means in an atomic scale, long range means over across the tens or hundreds of the atoms, that means the long range. So that means the long range ordering of atomic moment means all spins, one spin is this direction, and the other one has a pointing the quite similar direction. That's called the long range ordering. If they ordering in a very small length scale, like a few atomic distance, that's called short range ordering. But in a ferromatism, we are talking about the long range ordering. And that can be happens without external magnetic field. That's called spontaneous magnetization. But it sounds not so cringy, but if you think about the entropy, then entropy means the nature preferred the disordered state, not ordered state. So energetically, the in a previous sentence means this statement means the energetically more ordering state is favorable. That's the not quite correct for the thermodynamics. So the understanding of this unexpected phenomena is very important in a solid state physics, and this origin of ferromagnetism, which we will learn, is quite questionable. And in a ferromagnetism material, see this left cartoon, you can see it's quite similar to the previous one. This cartoon is quite similar one to here. Here, they will show about the ferromagnetism. In a ferromagnetic material, there's some critical temperature called the Curie temperature. Above the Curie temperature, the ferromagnetic material behave like just the paramagnetism. So the magnetic moment is increased with the external magnetic field linearly. But if we cool down the sample, of course, some critical temperature called the Curie temperature, they are not anymore the linear. They have some kind of curvature. And if you see here, we have a certain amount of magnetic moment even without external magnetic field. And if we have a much smaller temperature compared to the Curie temperature, there are a certain amount of magnetic moment with the without external magnetic field, and this magnetic moment is slightly increased with the external magnetic field, and so on. So if you plot this magnetic moment as a function of the temperature, they have a certain value and decrease, and finally going to zero at certain temperature. That's the Curie temperature. That's the very typical behavior of ferromagnetism, and this non-zero magnetic moment at final temperature is the necessary condition for the ferromagnetism. Okay, and here, please keep in mind this view graph, this class. And the next one is also the response of the external magnetic field of the B field, or that's the sum of the external field plus the magnetic moment. So in this kind of graph, it looks like similar to this one. But this one here, the field is quite large scale compared to this plot. Here, the H field is something here, very small scale. And here, the Y scale, here is the saturation magnetic moment. But here, the Y-axis is just magnetic moment, or the V field. The difference point is, in this plot, this Y value is kind of material parameter. So when you have a certain temperature and certain magnetic field, you can define the magnetic saturation moment of your material. But this response came from the internal structure of the magnetic material. That's what we call the domain. And technically, usually we see this kind of graph in many places. But in this kind of plot, experimentally very difficult to see. We need a very huge field, and this magnetic moment usually we assumed the constant in most of material. So they this plot, sorry, this plot represent a very global property of the ferromagnetic material, while this plot represent the some how can I say? Yeah, this plot represents the details of behavior of the ferromagnetic domains, not the material parameter. Maybe very confusing for you, but after you learn more about this, we're gonna figure out. Ferromagnetic material, we can divide two types. One is called the soft ferromagnetic material, and the other one is hard one. Actually, we have two image curve here. Actually, they are same one. I just make a different aspect ratio. They came from the same one. I just make it very make the small size for the y direction, the x direction, but increase the y direction. And this one is the typical image curve shape. And this kind of material we call the soft one. That means the soft means if you apply the magnetic moment, the state of magnetic moment is very easily changed. So this kind of material is very useful for the sensors or inductors or transformer. And in this ferromagnetic material, smaller HEC. The HEC means I didn't mention. Sorry. In previous case, this image curve, when you apply this strong enough magnetic field, the all magnetic moment inside the ferromagnetic material pointing the same direction. But if you decrease the magnetic field a little bit, zero field, zero magnetic field, they formed certain form of the domain. And some domain means the direction, some region where the magnetic moment direction is the same. So this is one direction, one domain, the other is the other domain. And this is another domain. And in a zero field, they form such kind of several domains. That means the average value of the magnetic moment is smaller than the saturated value. And if we apply the negative field, means this direction, and with the external field of this direction, this domain energy is lower. So they try to enlarge the area of this direction of domain. So at the certain field, the total magnetic moment is getting zero, like here. So that's we call the Cosby field. Okay. So Changang asked the question about the yeah, this is not quite a correct statement. What I'm saying is, in physics, more ordering state is energetically not favorable. But the ferromatic material, this kind of ordering means that's the energetically stable state. So it is not favorable in generally. So this is a kind of question: why this ordering state is more energetically favorable? In order to understand why the ferromatic state is stable, we have to understand this statement. Is it okay? Okay. So if you have more explanation, yeah, you can come to me and I will let you know. Okay. So now I just briefly explain this MH loop. So we'll learn it again. So don't be afraid about this. And if we categorize the material, two types, one is soft and is hard, what I'm explaining. And in a soft material, we need a very small field to reverse the magnetism direction. So that's the meaning of the small HC. It is very important in many applications, industrial applications like design of sensors and the transformers and so on. And in a hard magnetic material, which one we call usually the permanent magnet, is classified as hard magnetic materials. And compared to this soft magnetic material, they require a large cosmic field. But usually the MS value is smaller. In a permanent magnet, we need a large HC and with the large MS. But generally, if we make the hard magnet, we obtain the not that large MS. And also, it is important to also recording media like hard disk drive and some recording materials. And the important thing in a hard magnet, for the figure of merit is the larger product of the MS and HC, that's called the energy product, is desired. So this MS multiplied HC means this area. And the unit of this area is energy per volume. So that's what you call the energy product. And if we have a large energy product, means good permanent magnet. And I just briefly explained the performance of the ferromagnetic material, the permanent magnet. There is no direct relation, but okay. We learn about the relation of the HC to the MS. This equation, we're gonna learn about this. This is called the analyzed field, and this one is related to the HC, not one-to-one relation. And this relation, we assumed many things. With such kind of many assumptions, HC and MS is inversely proportional. But the truth is, the important thing is Ku, which one is called anisotropy energy, and this will determine this energy product mainly. But there are many other parameters affected this relation. So experimentally, this HC is determined depends on many parameters. So when you talk about the energy product, they are using the measured value of these two independent values. But if design the permanent magnet with the large HC, usually you need a small MS. So if you understand this relation, if you have a given material with the given Ku, NFP energy, and if you have a smaller ms, you can obtain the large HC. You can see this result in a ferromagnetic materials. In a ferromagnetic material, in certain temperature, ms value is very, very small, and it causes the large value HC. That's the such kind of relation. But in generally, those two quantity is not can I say not controllable separately. If you control one material parameter and the other one is affected. And explain about the KU yet. Are we gonna explain KU in maybe few minutes later? So in this stage, it's not easy to explain more details. Yeah, this part is kind of introduction, so don't be so much serious. If you didn't understand some part, I'm gonna explain later. But please keep asking questions. That's good. So in a permanent magnet, as I said, this part, energy product, is very important. And the energy product of each ferromagnetic material, like I explained such kind of magnet in a previous class. For example, ferrite is invented about 17 years ago. The energy product of those ferrite is less than 100. And 50 years ago, there are some kind of new magnetic material called samarium cobalt. And the energy product is a little bit over the 200. And NdIon boron, which one is the strongest magnet, the energy product is order of 400. So such new type of permanent magnet, there are many new applications become possible. For example, if you have a better magnet means you can obtain the better motors. So you have some experience with a very strong motors like a vacuum cleaner or screwdriver. They have a very strong. That can be possible because of the such strong good performant magnet. And also, if you imagine the electricity generator, you may know the electricity generator is quite similar to the motors. So that means if you have an improvement of 10% of performance in permanent magnet, you can generate 10% more electricity. Just imagine how we pay the cost for the electricity. If you have a better permanent magnet, yeah, you can decrease the cost of the electricity and you can save the environment and many things. So making the better permanent magnet impact is very large. So people keep going to find the better magnets, but so far it's not very successful. So the best permanent magnet was invented, 40 years ago, and there are many sister permanent magnet based on the NdIon boron, but there's not very successful achievement in finding a new permanent magnet. There are many new approaches using the nanotechnology, but some people claim that they found a very nice and very good performance of permanent magnet. But usually that is possible for the very small size, like nanoscale, not the macroscopic scale. But many applications for the permanent magnet, we need macroscopic magnets. So if you have an idea to make a good permanent magnet, it is very important in industry. Okay, so this is the end of the first part of my talk for the basic of the magnetism. So before moving to the next view graph, next PowerPoint, if you have any question, please ask me. Okay. Yeah, Gina just asked about the analytical magnet. The analytical magnet is, I think nowadays, it's not, people didn't use the analytical magnet anymore because its performance is not so good and the cost is not very cheap. So, but in some magnet, like samarium cobalt, is still used because they have a very large Curie temperature compared to ND-ion boron. So they have some benefits, but Anlico is not very popular. I didn't know. I'm not 100% sure, but it's not. I think it's only the old technology. Okay. So from now on, I'm gonna talk about the origin of the magnetism in a sense of the classical physics. So we need some simple math to understand the magnetism. So if you have some problem to understand this mathematical expression, please let me know. And if you need some extra explanation, yeah, maybe I can give it more. Okay. The origin of the magnetism, I already mentioned several times. The spin is because of the spin moment. The magnetism came from the spin moment of the electron. And this spin means very strange and difficult to understand object because the spin of the electron is actually came from the relativistic quantum mechanics. Classically, we can explain the meaning of the spin. It's just in a very simple way, but it is not quite correct. And even when we introduce the quantum physics, spin is still not very easy to understand. In order to understand the spin correctly, you need a Dirac equation of the electron, and that means that we need the relativistic quantum mechanics. But without such difficult physics, we can still easily imagine the property and the property of the spins. And also, we need to understand about the orbital moment we represent L. Because the motion of electron also contribute to the magnetism in a solid state. And also the total angular moment, the sum of the spin moment and the angular moment is also important. Okay, before going for the spins, let's recall the very basic part of the magnetism. Let's assume there's some kind of current loop here. There is some current passing through this direction. Here I is current. And in a side view, this loop, you can see this kind of side view, and this is top view. And let's think about the force acting on this rectangular loops. And now we assume the magnetic field direction is going down to the screen or from the top to bottom in this side view. Okay. We already know about the force acting on the wire with the current I. Yeah. I hope you remember this relation. This came from this Lorentz force. Okay, with this force, we have a current here, and minus field is perpendicular to this current. The force acting on this segment, called F1, is this direction. And you can easily imagine the force acting on this segment is F3 is pointing the other direction. And F2 is this direction, F4 is this direction. And F1, F3, they are same magnitude, but different direction. And F4 and F4, I'm sorry, F2 and F4, they are same in a magnitude, but different direction. So all this F1, F3 have this current I and the length A and the minus field B, and F2 and F4 are same for I and the length B and B field. And because of this cross product, we have a sign term here. And in this side view, you can easily see F1, F3 acting on this side. And even though they are same and the opposite direction, they are cancelled out. So the total force acting on this loop is going to 0. But the acting point of this force are not the same. So we have a final torque. We have a torque, which one is represented by the distance cross the force. Yeah, if you are not familiar with this torque, you should take a look the textbook again about the fundamental physics or the classical mechanics. Okay, and F2 and F4, they are acting in the same axis. The contribution of torque to F2, F4 are just cancelled out. And the torque is the sum of this all two force. We have a sum of the F1 and F3 here. And actually the magnitudes are same, so we have a factor 2 here. And the R cross F1 give you the F1 is here, and R is this is the length B, and this is half B, and the angle theta between the R vector and F vector, the sine theta here. So we have a cancelled out of 2, and we have a current I and B field. Here, the A multiplied B means the area of this rectangle. So we can define the magnetic dipole moment called mu by the multiplication of the current and the area. And the torque is expressed by magnetic moment multiplied by magnetic field. That's the torque acting on the magnetic moment of the magnetic field B. And this is quite similar to the torque exert in an electric dipole moment. This is the torque on an electric dipole moment. And this definition is very this expression is very important to understand the magnetism. Let's recall this is the current multiplied by the area. So here I want to recall, just a moment. Okay. So please keep in mind, the arc moment unit is the current multiplied by the area. In that sense, if we have a such kind of current in a ring, we can define the moment by the current multiplied by area. Here, area is nothing else but pi r square of the circle, if the radius is r. And this mass moment, if we have such kind of a running current, we have some magnetic field from this current. And let me ask one question. If you assume there is some black box, okay, let me make it clear. Yeah, let me ask a simple question. If you have such running current inside of the some box, you can measure the magnetic field in outside of the box. And also, if you have such small magnet and inside of this same box, and there's a magnetic field. Okay, so there's one and case two. This measured magnetic field is exactly same. Can you distinguish these two physical cases, case one and case two, from the outside of the box measurement? That's very conceptual question, but in physics, we need measurement. In order to distinguish some phenomena, we have a different measured value. But in these two cases, we cannot distinguish these two cases in any kind of measurement. Yeah, we just ignore the mass or some things, but if we measure just the magnetic field, we can make exactly the same one. So that means they are actually equivalent in the sense of the electromagnetism. So all running current of this shape is equivalent to the small ferromagnetic material, the small magnets, and vice versa. So we don't need to understand both. We need, if you understand a single one part, we can replace the other one. That's the very important concept. That is very important comment. Do you have any question about this? Yeah, let me give another example. Maybe you heard about that. If you have some rocket in the top of us, and you feel some gravitation by the gravitation acceleration. And if we have a same rocket and they are accelerate in a same magnitude, and if you do some experiment inside of this rocket and this rocket, they generate exactly same result, any kind of experiment. That means this acceleration is equivalent to the gravitation. That's nothing else but general. So experimentally, these two cases are exactly equivalent, so we can assume they are same physical phenomena. Okay, so if you set this, okay, let me move on. Yeah. Let's define the gyromagnetic ratio, gamma. That's the definition is, as I said, this circular motion is related to the magnetic moment. And this circular motion we can represent by the angular moment. Angular moment. So we can define the relation between the angular moment and the magnetic moment. That's called the gyromagnetic ratio, gamma. And we already know the magnetic moment of this circular motion is current I multiplied pi r square. And the angular moment of this electron, if you assume the mass m and velocity v and the radius r, then because the running current I is defined by charge E and the time period t, and we have a relation Vt equal 2 pi r. So current I is nothing else but this expression. So with this relation, we can obtain the gyromagnetic ratio, charge E divided by 2m. The important thing is m is mass of electron and E is charge of the electron. And the radius which determine this motion or orbital is dropped out. And this is very fundamental quantity of the electrons. So you can easily understand this gyromagnetic ratio came from the very fundamental physical quantity. It doesn't matter of the current and the details of the orbit. So now free electron can usually you can easily obtain the value of gamma here. And also, if you think about this motion of the electron, we have an angular momentum of this direction. But we have a negative charge for the electron. But in this expression, we assume the positive charge. The current means the positive charge. So the magnetic moment direction is actually the opposite to the angular momentum. So we have a negative relation between these two quantities. And let's think about the motion of this angular momentum with the magnetic field. Let's back to this one. So we determined the magnetic moment with the running current and the area. And the torque acting on this magnetic moment is we call this mu cross B, the torque. So let's back to here. With the magnetic field, these two forces generate certain amount of torque here. Sorry, this is the magnetic moment. Yeah, if we have a force here, actually there's some kind of a torque to this direction. So now we have a torque of this direction. So there's some rotating exist. So that can be expressed by relation. And here, if we have assumed this ring of the motion of the electron, and in that point, the velocity of the electron is this direction. And we assume the magnetic field of the g direction. And as a result, we have some force here. It's the same here. If we have an electron here, the velocity v field is g. Sorry. Okay. Okay, so this electric motion, this circular motion represented by this angular momentum or magnetic moment of this direction. So if you think of this relation, we have a certain amount of torque here. Or if you think about the motion of electron in this point, they have a certain amount of force here. And if you think about the electron here, they have a force in this direction. Because the velocity is v, v is here, so we have opposite direction to here to here. So as a result, they are starting to rotate. Okay. So as a result, if you have an angular momentum here, oh sorry, this is the weak field. And if you have angular momentum here, they have a certain precession. That is called Raman frequency or Raman precession. And in that case, the frequency of this motion is given by this relation. Here L is the angular momentum, so we have this relation. And this gyromountain ratio gamma is charge E divided by 2 mass M. So that means this frequency, called the Raman frequency, is proportional to the external magnetic field, and this is a given constant. Okay. And this value, the Raman frequency for 1 Tesla of the magnetic field is given by 14 gigahertz. Here, the important point is this unit. That means if you apply the magnetic field order of 1 Tesla, the electron, the magnetic moment because of the electron, the motion is precessed in a frequency order of 10 gigahertz. That's the meaning. The electron and the spin dynamics is order of gigahertz dynamics. So that requires many things because it's very fast motion. 10 gigahertz is quite high frequency. So it is you need to understand about this microwave dynamics to understand the spin dynamics. Okay. So just keep in mind, if you have a magnetic moment, here I just say angular moment, but it's same to the magnetic moment. If you have a magnetic moment here and external magnetic field, they are precessed. And this angular momentum, actually, we have such kind of a small motion of electrons. So electron motion is precessed because of the magnetic field. And this concept is very important to understand the spin dynamics. We call the Landau-Lorentz equation, basically similar to this motion. Okay, so I think before going further, I think it's time to question. Now it's time for the question and comment for today's lecture. Ask some questions. You mean this one? Okay. This cartoon is quite good to understand the details. Just a moment. Okay, so in order to understand this cartoon, yeah, this red circle means the motion of the electron, and as a result, we have a finite L here. And because of the magnetic field, there is some force, exerting force here, and as a result, the electron is little bit changed. And then the direction of L is a little bit changed in this direction. And so on. So this circle represent the end of the angular momentum because of the precession. Okay, so let me keep going to explain back Victor's question first. So this is the extreme case of the this case. Here, if you have a L is in this direction, L generates this motion, circular motion in this plane. But if L is the certain angle, the theta, they have such motion. But if the theta is 90 degree in this form, they are rotating in this motion. This is the case. The L is here, but with the magnetic field, they are rotating in this form. And at the corresponding motion of electron is the corresponding motion of the electrons for this one, for this one. And for example, if L is here, the electron motion is confined in the YG angle, like this. It's very confusing. It's a two-dimensional drawing. So if it is three-dimension, you can more easily understand. So, did you get more sense, more understanding? More. The last question. Yeah, your question is right. The first thing you have to need precession motion of the electron with the magnitude of 1 Tesla. But that is for the free electron, not the state. That's the important thing. Sorry. Okay. Gina, is it okay? Victor, is it okay? Yeah, I'm sorry about this poor cartoons, but yeah, if we have a kind of good animation, it's more easy to understand. But unfortunately, now I have only these two poor cartoons. Yeah, maybe it is good idea to implement. Now, can you see the some YouTube clip? It's so fast. Just so fast. Yes. Yeah, I just that's not yeah, you can find such a video clip. I just use the keyword of the Lama frequency. Uh, yeah, if I can find the better video clip, I will show you. But now I need to find the Google. Yeah, actually, the important thing is this part. This part is on. I want to show this part to understand why the precession happens. But as a result, this motion is the result of this is this cartoon is the explanation of the origin of the Raman precessions, and as a result, you obtain such kind of precession. Please ask more questions. Changgang, I'm sorry, I didn't understand your question quite well. Can you use the microphone and ask the question by Korean? Changgang, please use the microphone. Okay, so actually, I think your question is related to the resonance frequency, not the Raman frequency. The resonance frequency means if you have how can I say, natural frequency of your system, and if you apply the external disturbance with that specific frequency, the system response is very strong. That's the called the resonance. And in that sense, that resonance frequency is related to the system's internal energy. So in that sense, if we think about this precession, maybe you are thinking about the FMR. If you have a ferromagnetic material, and there are many kinds of internal energy inside of the ferromagnetic material, like anisotropic energy and exchange energy and dipole energy, and all energy can be converted by the effective field. And all sum of the sum of the all energy make some effective field in certain direction and certain amount. And then the electron spin is internally precessed around that effective field with that given frequency. So if we apply the various external magnetic field with the different frequencies, if the frequency of the external magnetic field is well matched with the internal frequency of the spin precession, the spin can easily absorb the energy from the outside of the magnetic field. That's what we call the resonance. So this resonance frequency is quite closely related to the internal energy. So maybe that's your question. Okay. So for this question, the definition of the gyromagnetic ratio gamma is relation between the angular momentum and the magnetic moment. But that is the free electrons. But in the solid state, the definition is changed to total angular momentum. So this is not anymore L, but they replaced by the J. That is the sum of L plus S. And in solid state, the S is came from the electron, L is came from the orbital moment. So in many 3D metals, the angular momentum is quite small. So they usually spin moment. The total moment is spin dominantly by the spin moment, but there is a small contribution from the angular moment. So depends on the materials and the details of the electron structure. This value is a little bit changed, but this value is almost 2 point something. So the difference of the gyromagnetic ratio for each material represent different contribution of the angular momentum of each material. Okay. clear? Okay. Question is about here if you have a small links with a large current and large links with the small current. Yeah, if we measure the mass moment from this behavior, only we can distinguish this value. So that means if you keep this relation, those two are not distinguishable. We cannot distinguish them. But it's very good question, yeah. Okay, thank you, Victor. Good. Yes, yes, you are right. We have a orbital magnetic moment and a spin magnetic moment, and we need a sum of those two, the total angular moment. The domain structure is quite complex in generally. If you have a three-dimensional samples, domain structure is always three-dimensional. But if you play with very thin films, ultra-thin films, the domain structure is usually two-dimensional. We're gonna learn about this domain maybe 2 or 3 weeks later. Thank you for your good questions, and I think today's lecture we should close today's lecture and see you at Wednesday. I already uploaded the one more lecture note in LMS. Please check it out. Okay, if you have more questions, you may using the Kakao or you may send an email to me. Thank you for your attendance. Okay, bye. See you Wednesday.